Welcome to Lecture 11. This is section 7.2 on trigonometric integrals. And before we jump into what's here, I want to actually solve for you the integrals for all 6 trig functions. So I'm going to add a blank page in here. And let's quickly talk about the integrals of the 6 trig functions. So number 1 would be the integral of sine x dx, which we know the antiderivative of sine is negative cosine x plus a constant. Totally fine. Integral for cosine is similar. Antiderivative of cosine is just positive sine x. So those two are fine. Okay. Next two, let's talk about tangent and cotangent. So the integral of tangent x dx. So typically our strategy with trig functions, particularly when they don't have powers, is that we want to convert to sines and cosines. So we're going to change the tangent to the sine of x over the cosine of x dx. From here, we're going to use a u substitution. So, and I typically u sub for denominators, because if I u sub for the numerator, then my du is going to be in the bottom, and that's not going to work well. So u is going to be cosine x, and du is negative sine x dx. So negative du is positive sine x dx. So that when we sub that, that becomes negative the integral of 1 over u du. And that gives us negative natural log absolute value of u plus a constant. And then we're going to switch back by plugging in our cosine. So we get the negative natural log of cosine x plus a constant. Now the other option here, so this is totally fine. Perfectly acceptable answer, but using my log rules, I can put this negative 1 back up on here, right? And so that's going to give me the natural log of cosine of x to the negative 1, which is 1 over the cosine of x, right? And 1 over cosine x we know is secant x. So here's another option for the integral of tangent. If you look it up, it's likely to be the lower one, like the latter one here, the natural log of secant x. But the negative natural log of cosine x is exactly the same thing, right? There's just a little algebra difference. Let's see. Let's get another page in here. The next one is going to be cotangent x, and it's going to look almost identical to what we just did. So the first thing we're going to do is switch to sines and cosines, and cotangent is the cosine over the sine. And so this time I'm going to u sub for the denominator, which is sine x, and its derivative is cosine x dx. So there's no negative here. We just get the integral of 1 over u du. The antiderivative here is the natural log absolute value of u plus a constant. And then we get the natural log of sine x plus a constant. Okay, and that's my antiderivative for cotangent x. Secant and cosecant are a little bit tricky, but they're also u subs. So when we have the integral of secant x dx, first thing we do is, actually we're going to leave it as secant x this time. And I'm going to take this and I'm going to multiply it by something very specific. I'm going to multiply it by secant x plus tangent x over secant x plus tangent x dx. Okay. And I do this because it works, okay? You wouldn't know that this is what you have to do, except that I'm telling you this is the thing we multiply by. And of course, we're not changing the integral because you're multiplying by 1. So if you distribute the secant x, and we distribute it into the numerator only here, you get secant squared x plus secant x tangent x. And on the bottom, I'm going to flip the order there to make it tangent x plus secant x dx. And now, just like before, I'm going to use a u substitution, and I'm going to u sub for the denominator. So that's the tangent x plus the secant x. And when you take your du, the derivative of tangent x is secant squared, and the derivative of secant x is secant x tangent x. And so notice that that is exactly what I have in the numerator. So this becomes the integral of 1 over u du, which is the natural log of u plus a constant. And we sub back in. So it's the natural log of tangent x plus secant x plus a constant. And that's my integral of secant. Cosecant is going to look almost identical. So we're going to take cosecant x, and we're going to multiply it by the appropriate thing. And the appropriate thing is going to be cosecant x plus cotangent x. And that's going to give us the integral of cosecant squared plus cosecant x cotangent x. And I'm going to flip the order on the bottom again. So that's going to be cotangent x plus cosecant x dx. And then we're going to make our u the denominator. So that's cotangent x plus cosecant x. And our du is going to be negative cosecant squared x minus cosecant x cotangent x. Notice that they're both negative. Factor out the negative and move it to the other side. So negative du is cosecant squared x plus cosecant x cotangent x. So when I make that substitution, the numerator is negative du, so negative du, and I get 1 over u. And so I get negative natural log absolute value of u plus a constant, and we plug it in. So that's cotangent x plus cosecant x plus a constant. Now, I'm not going to do the same trick that I did with tangent, or was it cotangent? Whichever one it was above. It would have been tangent, right? Where I move the negative 1 up as a power and do 1 over. You can, but 1 over this sum isn't a new trig function, so it's not actually worth it to change anything. So in summary, you have that the integral of sine x dx is negative cosine x. The integral of cosine x dx is sine x. Integral of tangent x dx is the natural log of the secant of x plus a constant. The integral of cotangent x dx is the natural log of sine x plus a constant. The integral of secant x dx is the natural log of secant x plus tangent x plus a constant. And the integral of cosecant x dx is negative natural log of cotangent x plus cosecant x plus a constant. And there's the integral of your 6 trig functions, okay, by themselves. Notice that I didn't need any new techniques to be able to do any of those, okay? I did have to know what to multiply by for secant and cosecant, but the integration technique itself was just use substitution. From here, we want to be able to integrate things that are a little more complicated with higher powers. And so what we're going to need is our trig identities. So note, here are all your trig identities. And so the first few are your Pythagorean identities. So you've got sine squared plus cosine squared equals 1. And underneath, I just solved it for one of the trig functions. So cosine squared or sine squared. The middle one, you've got the tangent squared plus 1 equals secant squared, which you get from dividing that first one, the sine squared plus cosine squared equals 1, by cosine squared. If you subtract 1 from both sides, you get tangent squared equals. And then we've got this one, which you get from taking the first one, sine squared plus cosine squared equals 1, and dividing through by sine squared. That'll give you this identity on the right. If you subtract 1 from both sides, you end up with an identity solved for cotangent squared. Okay. Then you also have double angle formulas and double angle formulas. So for sine 2x, we get the 2 sine x cosine x. And from cosine 2x, we have 3 different versions because cosine 2x is cosine squared minus sine squared. And if you sub in from above, from your cosine squared plus sine squared equals 1, then you can get those other 2 versions. Okay. If you take those bottom 2 and solve them for sine squared and cosine squared, you get the ones that are over here. So these are all the potential trig identities that we're going to need. Okay. I'm going to unhighlight them for a second so that we can use them later. So where are these useful? Okay, they're useful when we start taking integrals of trig functions that have powers. And there's 2 techniques here. So what I notice is that I've got cosine cubed, and cubed is an odd exponent. So we've got odd exponent. When that happens, I'm going to separate this into cosine x times everything else. In this case, cosine squared. And I do that because, and I'm going to rearrange this for a second. I do that because I want this to be the derivative, right? I want to be able to use that as my du. So I want this to be du. But cosine is the derivative of sine, so I would need my derivative, I would need my u to be sine in order for cosine x dx to be my du. But right now I have cosines here. So how can I convert this to sines? Well, I can convert this to sines if I go up here and say, oh, okay, well, cosine squared is 1 minus sine squared. So that's the identity that I'm going to use. So I'm going to replace cosine squared with 1 minus sine squared. So I'm going to make this the integral of 1 minus sine squared x times the cosine x dx. Okay. If I distribute that, I get the integral of, distribute the cosine x dx, which we know, we just did that above, minus the integral of sine squared x cosine x dx. And from here, I can make that u substitution. So I can u sub for sine x, and my du is cosine x dx. What that does for me is the first one, the integral of cosine x dx, antiderivative here is just sine x. But then for my integral, I'm going to make this, the sine becomes u, so that's u squared du. And this becomes the sine of x minus 1/3 u cubed plus a constant. And then to get back to my x's, I substitute back in with my sine x. Okay, so notice how that works. So when it's odd, I pull 1 away from the rest. That's going to be my du. And I convert the others to the opposite trig function. So in this case, I converted my cosine squared to a sine squared. Okay, and depending on what power it is determines what identity we're going to use there. Okay, let's see what else we can do. Okay, here's another one. This time we have an even power. With even powers, I'm going to try to convert this using my double angles and half angle formulas. So this is the integral of sine squared squared. So I'm going to go up here for sine squared, and I'm going to go over here and use this one, right? Because sine squared is tricky to take the integral of, but cosine of 2x is not. So I'm going to use this one. So I'm going to replace my sine squared with 1 minus cosine 2x over 2. So this is going to be the integral of 1 minus cosine 2x over 2, and I'm squaring it. Okay. When I do that, squaring the 1/2 that's on the bottom there brings a 1/4 out front. And then I'm squaring 1 minus cosine 2x, and that gives me 1 minus 2 cosine 2x plus cosine squared 2x dx. Okay. Now I'm going to split this one up because I know some of these. So this is 1/4 the integral of 1 dx minus 1/2 the integral of cosine 2x. That one I can do, dx. Plus 1/4 the integral of cosine squared 2x dx. From here, now I've got another square, right? So, okay, what can I solve here? And I'm going to leave them all as integrals for now, and I'll integrate later. And I'm going to replace the cosine squared using that same kind of identity. So if we go back up, this time I'm going to use the cosine squared one. So it's 1 plus cosine 2x over 2. So I'm plugging that in here. So 1 plus cosine. Now, originally I had 2x, and now I'm doubling that to be 4x over 2 dx. So what we really get here is 1/4, and let me zoom in because I'm running out of room. 1/4 integral of dx minus 1/2 the integral of cosine 2x dx. Now I've got 1/4 times 1/2, so that gives me 1/8, and times 1. So plus 1/8 integral of 1 dx plus 1/8 the integral of cosine 4x dx. And now what I've done is I've made it into all things that I can use baby u subs or just integrate with. And so that means that my answer here is going to be 1/4 x, because the antiderivative of 1 is just x. All right, now when I take the antiderivative of cosine 2x, this is minus 1/2. And antiderivative of 2x, that 2x is a baby u sub, it's going to pop out a 1/2. And the antiderivative of cosine is sine. Plus, the integral of 1/8 just becomes 1/8 x. Plus 1/8. And when I take the antiderivative of cosine of 4x, it pops out a 1/4. Right, that's our baby chain rule. And the antiderivative of cosine is sine. And so if we clean that up, that gives me 1/4 plus 1/8. Let's see, double that. That gives me 3/8. So 3/8 x. And then sine 2x and sine 4x are not like terms. So I'm going to have minus a 1/4 sine 2x. And I'm going to have a plus 1/32 sine 4x plus a constant. Okay, so in this case, when I have squares, I use my double angle formulas. Sometimes I need them twice. Okay. Depending on what's going on. Okay. All right, here in number 3, I have all even powers. So what I'm going to do is I'm going to convert them both. Okay. So I'm going to have the integral of sine squared, and sine squared is 1 minus cosine 2x over 2. And cosine squared is 1 plus cosine 2x. 2x over 2 dx, because they're even, right? Even, we convert using our double angle formulas. From here, this is 1/4, bring out each of the 1/2s, and 1 minus cosine squared 2x dx. And this is the same as 1 minus, if I use my trig identity for 1 minus cosine squared, that's sine squared 2x dx. And then I'm going to use my identity again. So for sine squared, that's 1 minus cosine, and I double the angle. So it was 2x, now it's going to be 4x over 2 dx. That gives me 1/8 times the integral of 1 minus cosine of 4x dx, and now that's something I can work with. So this is 1/8 x minus 1/8 times, and cosine of 4x, we get a baby u sub, pops out the 1/4. Antiderivative of cosine is sine 4x plus a constant. So we get 1/8 x minus 1/32 sine of 4x plus a constant. Okay, so again, anytime you have all even powers, you're going to change everything to cosine 2x's, right? Use your double angle formulas. And if you end up with squares, you do that again. All right, and here's our last one for the lecture. This one has an odd power. Right here. So what I'm going to do is I'm going to pull one of those away to go with my dx. So sine of x goes over here with my dx. And I'm left with sine to the fourth x times cosine squared x. Okay. And what I get to do here is I am going to convert these to the opposite of whatever this is. So this is sine x, and I want that to be my du. And that comes from a u equal to cosine x dx. And I'll have to sort out the negative. It actually will go over here. But so I want the rest of this to be in terms of cosine. So I need to convert sine to the fourth into cosines. Okay, and so I'm going to use my, I am going to use my formula for sine squared, right? So this is really sine squared x squared times cosine x squared x times the sine of x dx, right? And so I'm going to replace that sine squared with 1 minus cosine squared. Now I'm going to use this u substitution over here that I was trying to use before. So if I let u equals cosine x, that means its derivative is negative sine x, and I move the derivative to over on the other side, okay? So that means my sine x dx is negative du. So I'm going to have a negative integral du. And my cosines all becomes u. So this is 1 minus u squared squared times u squared. And now I can sort out my powers, right? So this is equal to negative integral. 1 minus u squared is 1 minus 2u squared plus u to the fourth. And I'm multiplying all of that by u squared. So that is u squared minus 2u to the fourth plus u to the sixth du. Now we can distribute our negative. That's negative u squared plus 2u to the fourth minus u to the sixth du. Now we can find the antiderivative. So negative 1/3 u cubed plus 2/5 u to the fifth minus 1/7 u to the seventh plus a constant. And lastly, I plug my cosine x back in. So negative 1/3 cosine cubed, 2/5 cosine to the fifth, and 1/7 cosine to the seventh plus c. Okay, so again, when you have an odd power, we're going to separate one that I'm going to match up with a dx, and that's going to be my du, and I convert everything else to the opposite trig function. So the cosine squared is already opposite of sine. We just had to convert the sine to the fourth. Sine to the fourth is sine squared squared, and I can use 1 minus cosine squared to replace my sine x squared x. From there, we can make our u substitution and work it through and integrate. So moral of the story, when you're working with trig integrals and you have one odd power, okay, can be both odd, but as long as you have at least one odd power, you can separate one of those out and convert the others to all the same trig function, right? The opposite trig function of what you're picking to separate out. If they're both even powers, then, oh, and this should say double angle. We're going to use our double angle formulas to convert so that it moves our squares kind of inside the argument is what that does for us. Okay. And that's going to be the end of our lecture.